Sweta and I am from BSc Chemistry Honors 3rd year, and this is the chapter of Physical Chemistry named as Raman spectra. General introduction है Raman spectra का. It is a special type of spectroscopy which deals not with the absorption of electron but deals with the scattering of light by the molecules. It is observed that when a substance, which may be gaseous, liquid, or even solid, is irradiated with monochromatic light of a definite frequency mu, a small fraction of the light is scattered. Rayleigh found that if the scattered light is observed at right angles to the direction of the incident light, the scattered light is found to have the same frequency as that of the incident light. This type of scattering is called Rayleigh scattering. When a substance, gaseous, liquid, or solid, is irradiated with monochromatic light of a definite frequency mu, the light scattered at right angles to the incident light contained lines not only of the incident frequency but also of lower frequency and sometimes of higher frequency as well. The lines with lower frequency are called Stokes lines, whereas lines with higher frequency are called as anti-Stokes lines. Raman further observed that the difference between the frequency of the incident light and that of a particular scattered line was constant depending only upon the nature of the substance being irradiated and was completely independent of the frequency of the incident light. If frequency initial is the frequency of the incident light and Vs that of a particular scattered line, the difference del V is equal to Vi minus Vs is called Raman frequency or Raman shift. Thus, the Raman frequencies observed for a particular substance are characteristic of that substance. The various observations thus made by Raman constitute what is called Raman effect, and the spectrum observed is called Raman spectrum. This is in a simple way Raman spectrum may be represented. Explanation for observing Rayleigh line and Raman lines. When the incident photon hits the molecule, this collision may be elastic or inelastic. Elastic collisions means that the colliding particles will return with the same energy. Thus, the scattered photon has the same frequency as that of the incident photon. This explains Rayleigh scattering or Rayleigh line. However, if the collision is inelastic, still the law of conservation of energy will hold good. That is, total energy before collision and after collision must remain the same. Thus, some energy may be transferred from the incident photon to the molecule so that the scattered photon has low energy and hence lower frequency than that of the incident photon. This explains the occurrence of Stokes lines. Alternatively, some energy may be transferred from the incident photon to the molecule so that the scattered photon has higher energy and hence higher frequency than that of the incident light. This explains the occurrence of anti-Stokes lines. This explanation may be further elaborated as follows. When the photon strikes the molecule, the energy is absorbed by the molecule and it gets excited to some higher energy level. Now, if it returns to the original level, it will emit the same energy as absorbed, and thus we have Rayleigh scattering. However, in most of the cases, the excited molecule does not return to the original level. It may return to a level higher than the original level, thereby emitting less energy than absorbed. This explains the occurrence of Stokes lines. Thus, a part of the energy of the incident photon remains absorbed by the molecule, so that the molecule has higher energy than before. Alternatively, the excited molecule may return to a level lower than the original level. Thus, more energy is emitted than absorbed. This explains the occurrence of anti-Stokes lines. In this case, the molecule has less energy than before. The different cases may be represented diagrammatically as shown. Levels have been shown equally spaced just for the sake of convenience. So this is the diagram: energy absorbed by the molecule, Rayleigh scattering, polarizability of molecules, and Raman spectra. The Raman effects arises on account of the polarization distortion of the electron cloud of the scattering molecules that is caused by the electric vector of the electromagnetic radiations. The induced dipole moment mu depends upon the strength of the electric field E and the nature of the molecules. We write mu is equal to alpha E, where the quantity alpha depends upon the nature of the molecules and is called polarizability of the molecule. Thus, polarizability is the ratio of induced dipole moment to the strength of the electric field. In case of atoms or spherically symmetrical atoms, spherical rotors such as CH4, SF6, etc., same polarizability is induced whatever be the direction of the applied electric field. They are said to be isotropically polarizable. Such molecules are said to be isotropic molecules. In case of diatomic molecules, homonuclear or heteronuclear or non-spherical molecules, the polarizability depends upon the direction of the electric field. For example, in case of H2 molecule, the distortion produced is more when the electric field is applied parallel to the bond than when it is applied perpendicular to it. And we write alpha parallel is greater than alpha perpendicular. Such molecules are therefore said to be anisotrophically polarizable. Types of molecules showing rotational Raman spectra. A molecule scatters light because it is polarizable. Hence, the gross selection rule for a molecule to give a rotational Raman spectrum is that the polarizability of the molecule must be anisotropic. That is, the polarizability of the molecule must depend upon the orientation of the molecule with respect to the direction of the electric field. Hence, all diatomic molecules, linear molecules, and non-spherical molecules give Raman spectra. They are rotationally Raman active. On the other hand, spherically symmetric molecules such as CH4, SF6, etc. do not give rotational Raman spectrum. They are rotationally Raman inactive. These molecules are also rotationally microwave inactive. This is one of the reasons for the importance of rotational Raman spectroscopy over infrared spectroscopy, because the latter requires that the molecule must have a permanent dipole moment, whereas the former only requires that polarizability of the molecule must change during vibration. Explanation of Raman's effect in terms of polarizability. The polarizability alpha of the molecule that is rotating or vibrating is not constant but varies with the frequency of vibration or rotation. It is sum of two parts. Equilibrium polarizability alpha 0, that is the polarizability when the atoms of the molecules are in their equilibrium positions. Second sum of the polarizability of the molecule due to the various rotational and vibrational motions, each term depending upon the frequency of rotation or vibration. Alpha is equal to alpha 0 plus summation del alpha n by del r bracket r n cos 2 pi v n t, where alpha n is the polarizability associated with the nth rotational or vibrational mode and Rn is the maximum displacement of the atoms involved. E is equal to E naught cos 2 pi V naught t. Substituting the values of alpha and E from equations 2 and 3 in equation 1, we get. This expression consists of three terms. The first term has the frequency of the incident radiations and represents Rayleigh scattering. The second term contains V0 minus Vn represents Stokes lines, whereas the third term contains V0 plus Vn and represent anti-Stokes line. Quantum theory of pure rotational Raman spectra of diatomic molecules. The selection rules for pure rotational Raman spectra of diatomic molecule are del J is equal to 0, plus minus 2. The selection rule del J is equal to 0 corresponds to Rayleigh scattering, whereas selection rule del J is equal to plus minus 2 gives rise to Raman lines as explained below. We know that the energy of a rotational level in terms of wave number with quantum number J is given by mu bar is equal to Bj into my J plus 1 when a transition takes place from a lower rotational level with quantum number J to a higher rotational level with quantum J dash. The energy absorbed in terms of wave numbers will be for the selection rule and again for the selection rule. So here are the second, third and fourth equation. Combining the results of equation 3 and 4, the wave number of the lines obtained in the Raman spectrum will be given by how here mu I represents the wave number of the Rayleigh line, plus sign gives line with higher wave numbers called anti-Stokes lines, and minus sign gives lines with lower wave number called Stokes lines. From equation 5 it may be seen that J is equal to 0. The first Stokes and anti-Stokes line will be at a separation 6b from the Rayleigh line. Further putting J is equal to 1, 2, 3, the separation between any two adjacent Stokes lines or anti-Stokes lines will be 4b. Thus, the pure rotational Raman spectrum expected for a diatomic molecule may be represented. 3.39 Intensities of lines of the pure rotational Raman spectra. As explained earlier, the intensities of lines depend upon the population of initial level from where the molecules are excited or de-excited to the final level. Since the population of rotational energy levels is shown, therefore the intensities of the Stokes and anti-Stokes lines vary in a similar manner. Application of pure rotational Raman spectra. From the pure rotational Raman spectra, noting the separation between the lines, the value of B can be obtained, from which the moment of inertia and the bond length of the diatomic molecules can be calculated as explained earlier. Quantum theory of rotational vibrational Raman spectra of diatomic molecule. 3.41 For large molecules, the lines obtained due to rotational transitions are so weak that they are beyond resolutions. Hence, we have a pure vibrational Raman spectra for which the selection rules are same for pure vibrational spectra discussed earlier. However, in case of diatomic gaseous molecule, the resolution of rotational fine structure is sufficient and can be studied. Thus, diatomic gaseous molecules give rotational vibrational Raman spectra, which can be explained as follows. The selection rules for the transition are del V is equal to plus minus 1, del J is equal to 0, plus minus 2. However, at room temperature, as most of the molecules are in the lowest vibrational level, V is equal to 0. Therefore, the significant vibrational transition is from V is equal to 0 to V is equal to 1, called fundamental vibrational transition. Restricting ourselves to this vibrational transition only, the results obtained are as follows. We have considered the case for del V is equal to plus 1, which represents Stokes lines. The anti-Stokes lines are those for which del V is equal to minus 1. They are usually weak because very few molecules are in the excited vibrational state initially. The rotational transitions accompanying the vibrational transition from V is equal to 0 to V is equal to 1 and the rotation vibration Raman spectra obtained may be represented. Advantages of Raman spectroscopy over infrared spectroscopy. Raman spectroscopy has a number of advantages over infrared spectroscopy as briefly explained. Since Raman frequencies are independent of the frequency of the incident radiation, hence by suitably adjusting the frequency of the incident radiation, Raman spectra can be obtained in the visible spectrum range where they can be easily observed rather than the more difficult infrared range. Raman spectra can be obtained even for molecules such as O2, N2, Cl2, etc., which have no permanent dipole moment. Such a study has not been possible by infrared spectroscopy. Raman spectra can be obtained not only for gases but even for liquids and solids, whereas infrared spectra for liquids and solids are quite diffuse. Because of the ease with which the Raman spectra can be studied, the molecular structure of the large number of compounds have been determined by Raman spectroscopy. However, infrared method still continues to remain popular. This is the experimental arrangement for Raman spectra, and this is the diagram or apparatus. The fraction of light scattered is so slow that normally very weak Raman lines are observed. Hence, to detect these lines, it is necessary to use a powerful source of incident light. Earlier, mercury vapor lamps were used, which gave an intense monochromatic radiation of wavelength 4358 angstrom, 435.8 nanometer. However, with the development of lasers, which are very powerful sources of monochromatic radiations, Raman spectroscopy has been greatly revolutionized.